Thank you. That was a very kind introduction of you. Can you hear me okay? Like everybody else, I'll be using the Blackboard. I don't have particularly good writing or large, so if you can't understand some of it, just stop me and ask me about it. But that's also the reason why the lecture notes for these lectures are already available online. So you can have a look at them, and if there's anything unclear, maybe compare with those, or have that by your side. However, please do keep an eye on now that's on the Blackboard for the things that we'll be talking about that sometimes will be slightly different. Writing. So it's good to start with a title. And this is the assignment I've been given. I've changed slightly the title, but it's still the same at heart. It's down to calculate in EFT. And so I prepared the lectures for this topic, for this school, which means they were tailored to the kind of input that you have from other lecturers, and they try to be complementary. In particular, the focus in here will be workshop-like. So I'll give you typically very concrete, simple examples that you can work through. The idea is teach yourself how things work, rather than being told this or that works like that. I remember a while ago now, but when I was a student, sitting in a school like you, if I now think back of what I learned from there, the things that are most clear are the actual computations that I did at the time to understand things. So that's why I hope you can work through the problems. I know there's a lot of other lecturers teaching you things and demanding your time, but if you can just invest a bit of time into it, you'll get something in return. Very good. And for that matter, in the notes, you'll have the problems. So the problems are not on separate paper, but they're on the same notes and they're marked in purple. Some of them will partially work through in the board, and then I'll ask you to solve them the rest of it. Or at times will be problems that we won't have time to cover, but if you have the extra time now or later in the future, you can work through them, and at some point I can give you the solutions if you want those. Very good. Useful references for these lecture notes, some of them I've used in building my notes, are the EFT lectures by Anish. And also, they're not on the archive, or I couldn't find them, but you can find them online. There's also EFT lectures by David B. Kaplan. Which are somewhat different from Anish's, but it's complementary and good. And I'll use some of the example headed. In addition, there's other references I'll pull from. They're in the notes, and you can look at them yourselves. Some of them are historical, some of them are practical for the type of things we'll be doing. But it's good to read about. I'm not too big on literature and citing everything that should be cited, so I apologize for that. But if you want to learn about more things, you can ask me. Like we said, this is a school in which you have all of your lecturers here, so there's chance for interaction and just talking off lecture time as well. Good, so what's on offer? Let me tell you what we'll try to learn in these lectures with, like I said, every one of them a given example. So today, on lecture 1, we'll look at features of EFT in, well, really quantum mechanics. So you don't need the whole machinery of quantum field theory to learn about how EFTs work. And in fact, if you go to quantum mechanics, you can work through the algebra much more easily. It's not as complicated, but also learn how these theories work. So that's what we'll do today. We'll cover a number of topics there as outlined in a minute. In lecture 2, we'll learn about model dependence and independence. Okay, in particular, we'll look at what we call matching. Again, with a specific example that you can work through. In lecture 3, we'll look at field redefinitions. You've seen a little bit of this already. Perhaps also unitarity if we have time. Lecture 4 will be about renormalization. This historically the reason why EFTs were thought to be inconsistent theories. Now we know that's not the case. So we look at renormalization. And in lecture 5, we look at anomalous dimensions. And operator mixing, if we have time. Very good. Some conventions for us to get it started. I won't put all of them in here. Some of them are in standard textbooks, but well, just to make sure we're on the same page, the metric will be the mostly minus. We're working in 4 dimensions, or 4 minus 2 epsilon. This might be trivial for you to look at, but it's good to remind yourself of what the quantized field is. This is a complex scalar field we're talking about here, and that will be some interval over phase space. Of some annihilation operator times e to the minus 4 vector x mu dot p mu. I'll write this explicitly now so that you know. And then the creation operator of the antiparticle e to the pi. In addition, something somewhat related but different, and it's good to know that it's different, is the Fourier transform of a field in 4 dimensions will be just the integral d4 p. If you want to use p, I want to use q actually. It's some factors of 4 pi. And then the Fourier transform will put a tilde on it, a function of q. And then we have I q dot. In addition, because, well, sorry about this, it's not standard notation, but partly because I'm a bit lazy about that, partly because we'll be writing it over and over again, loop integral. I abbreviate by these square brackets dl, and I'll just be d4l, or if we're in dim rec, dl 4 pi square mu 2 epsilon. It'd be also good to be familiar with the formula for dimensional regularizations. I'm not going to write it here. We don't quite need it yet, but it's in Anish's notes, for example, or, well, in Peskin in textbooks, you'll find it. And so what's in store for us today is lecture 1. I'm going to outline what we have. So I forgot to ask, is 55 minutes the lecture? So 1 hour. Okay, good. 1:35. Okay, good to know. Righty. So I probably won't have time to cover all of this material in lecture 1 notes that we have, but if you want to ask me about it later, please do. Right, in lecture 1, which is the simple QM quantum mechanics example, we're going to try and see already quite as much as we can actually about EFT. In particular, well, you've heard about it, but it's not bad to repeat the foundations of any EFT are. I'll use another color to emphasize. You have to identify the degrees of freedom that are relevant for the system. This might look like a triviality to you, but it's not always a triviality, and we may see an example in which it is not. Then you have to put into account the symmetries. Some of the community now calls what we used to call gauge symmetries redundancies in the description. So if you come across that, I'll just write it in here as well. Redundancies. And in fact, one can understand theory definitions in that context as well. And one of the crucial things is just crucial, but it permeates all of physics, is identify your expansion parameter. The crucial, some might say the crucial contribution from Wilson that told us EFTs are not sick. That's what you put in, what do you get out? So some of the features. Will be, well, it has a limited validity range, as you would expect of any theory. It's not valid everywhere. Any one theory you think of right now in nature probably has its own limitations. This feature of model independence or dependence, which we'll try to make a little sharp in there, and that's connected to matching, that we'll see today as well. Again, we now know that they are renormalizable. So the fact that we called higher dimensional operators non-renormalizable operators is a bit of a misnomer. They actually are perfectly renormalizable. And that also means that they are predictive. It's not that you have to keep on putting inputs into your theory to get predictions that are independent of any particular value. They can, in fact, be highly predictive. Some of these you might have already touched upon in the previous lecture, some of them not, but what we'll try and see today for pretty cheap, or somewhat cheap, which is to say solve a quantum mechanical system, a bit of degrees of freedom symmetries, your expansion parameter, of course, limited validity, and model independence. Because with quantum mechanics, you won't get to see any renormalizability properties in there. Very good. So let's get going with it. Now we're going to talk about quantum mechanics. Remind yourselves about wave functions and all of that in one dimension. You cannot get much easier than this. But before we go there, any questions about notation on any of the things I've introduced? Alrighty, good. I know you're all proficient in QFT, but nevertheless, I will go through details at times. Don't worry, I'm not going to rush through computations, and you should stop me if you don't understand something. Alrighty, here we go. We're going to look at scattering in one-dimensional quantum mechanics. We're going to solve a one-dimensional system. It's going to conserve energy. So we, in fact, only have to solve the time independent Schrodinger equation. And as we'll see, that already contains quite a bit of information. This example, I should say, most of it, I lifted it from Kaplan's notes. You can find more details there. So some things are different. Righty, so first, well, you have Schrodinger's equation in which you have to specify your potential. So we have to talk about what potential we'll be talking about and what does it look like. The first, we take several potentials and see how things work out. The first one will be the square well. In 1D again. And again, it's not really square, it's more like a rectangle, but anyway. It's going to look like this. That's the x-axis, the only one spatial dimension we have. The potential is going to be 0 for all x minus infinity. Yeah. It's going to be 0 for minus infinity. It's going to have, well, it's going to start at x equals 0. Have some value there to go back to 0 after a length L. And the depth of it is going to be 1 over 2 ml. M is the mass of the particle we're talking about in one dimension. If that's the case, well, now we have to sort of kind of specify our initial state. So we're going to send a particle coming out from minus infinity to encounter that well. That looks like at that, well, you can think of that time as a wave function that will be proportional to the square root of the flux, as to how much of how many particles are coming in. If you're thinking of a single particle, what is the fraction of the particle flowing through a given position in space? And of course, just solution for a free particle minus I energy times time is moving to your right. So it's I to the kx and energy minus energy times time. All of this is in natural units, so there's no h parts to be found in here. Well, as you know, the energy will be just k squared over 2m, so that free particle coming from the left. And now we're going to solve a Schrodinger equation for that. Hopefully that picture is clear enough. The actual, stepwise definition is in the notes, and I forgot, of course, factor of alpha square on top. Some dimensionless coupling in there. Righty, so the problem is not too complicated. The time independent Schrodinger equation will just look like the energy times the wave function is a free term time derivative, the space derivative, sorry, plus the potential. And we know how to solve this stepwise. It's not a big deal. But just to introduce notation, that partial x is what I'll call derivative with respect to x. If you do that, it's good to define, well, I'll use some index to talk about the wave function in the three regions. In the positive axis plus to infinity regions, I'll call this phi plus of x, where this now sort of has the factor of energy taken out. So this is time independent, but you can put back in the factor of e to the energy. It will be common to all of them. And in here we have a coefficient t times the exponential of e to the I k x. It's again, the potential is 0, so in fact in there we have k again, just like we had it in there. Right, in the right-hand side, or the left-hand side, sorry, we'll have psi minus, and that will be the original incoming wave in there, but we're going to divide everything by the square root of the flux, so that it's slightly simpler. For the algebra, that's going to be e to the I k x, the initial incoming flux, plus some coefficient r for the reflected wave, which is traveling backwards, so it's e to the minus ikx. In the middle, we'll have phi naught, which is just going to be some a e to the I qx plus b e to the minus I qx. Where in that regime, we have different momenta q, because there's that well in there. But within the world, it's just a flat potential, so the solution is also plane waves. Only now q squared, you can work it out, is k squared plus alpha squared over L squared. Another typo, there's an L squared in here. So that you do indeed get that L squared in there when you solve for it. Good, I should correct that in my notes. Righty, so with that, now we have, all that's left is to solve the boundary conditions. So this much I've sort of done for you. What I want you to try out, and again, this is a bit of time investment on your side that will be rewarded later. You just solve for the boundary conditions of this to find, in particular, what we're interested in is the coefficients R and T, for the wave that has made it through the well and the wave that is traveling backward. What are the boundary conditions? Well, they follow from looking at Schrodinger's equation. One of them we sort of put in here already, and is that wave function on the right only has one component. There's not the exponential of minus IQ x, because we assume there's no wave coming all the way from plus infinity. We started from the left. The other two are just connecting the wave functions in there and their derivatives, because the second derivative, as Schrodinger equation tells us, is discontinuous. The first derivative will still be continuous, and so will be the wave function itself. So what I want you to solve, let's mark this in purple, so there's color coordination between the notes and this. Your equation, so let's put it here. I want you to solve this simple quantum mechanical system in which, well, basically the wave function at 0 for left and right is the same. We call it 0, 5, 0. And so is the derivative. And the same thing holds for that other junction. 0. Psi plus 0. That's 4 equations for those variables left in there. T, B, A, for 4 variables, so you can solve it to find. And this is what I want you to check. I'm giving you the solutions, but please. Sorry? Yeah, sorry. So this. Oh, yes, very good. Very attentive. That's good. Yeah, sorry. I'm not the best at talking and writing. Yeah, this is a L. Right, and then your quantum mechanics system, the solution for this, you can check yourself. I don't care about phi naught in the middle, that you get phi minus and plus. It will be e to the I q x plus k squared minus q squared, k squared plus q squared minus 2I q k. The cotangent of QL. And then for psi plus, there's only one wave, and that reads minus 2q k e to the I k x minus L over a similar denominator. Okay. Cosine of QL plus I k squared plus q squared sine of QL. And this has the e to the minus kx. Right, if you get that far, then now you can think about those reflected and transmitted waves. The reflection coefficient is the square of r. Will tell us something about how much is coming back and how much is going through. And you can rewrite nicely r squared. If you think of this, this is like the non-trivial part of the scattering. What goes through is like just that nothing haven't happened. It just went through. So the only non-trivial scattering will be backwards in this case. And you can rewrite that with a little bit of work as 1 over 1 plus 2kq, the whole thing squared over sine ql k squared minus q squared, the whole thing squared as well. You can also compute t squared. I'll give you the transmission coefficient. But, and here's the first question for the audience. You can check this yourselves if you have the patience, or if you want to think about it. That's the question now. So t squared, you can find is 1 minus r squared. You can find that explicitly. We know t, we know r. You can do it. It's a bit of, a lot of q's and k's and cosines up and down, but you can work that out. But just if I give you this equation like that, can you think of a justification for that before computing anything? And yeah, so I will pose questions to the audience. If you don't mind speaking up, please raise your hand and tell the answer. But don't worry about getting it wrong. This is about learning, not about being right. But can anybody think of a reason why this is the case? Exactly, conservation probability. We said that this is about the wave that gets transmitted for that t coefficient and the one that gets reflected. So we had some incoming wave. The total probability, or the two ways that that probability can go, is back or forth. So the sum of them should be the same as what was coming in. And this is, again, you might realize that's pretty, if you work through the algebra, sort of easy to get, and that's just a version of unitarity, really, which is nothing but probability conservation. But what we really want to do in here, provided we have enough time, that we do, yes, is to actually take all of that complicated expression that cost us a bit to find out, and actually expand it on a Taylor series in the limit. Now we're going to expand in the limit in which the width of that well, L, is very small compared to the incoming momenta K. So we're going to span in L being much smaller. Remember, K in these natural units has the dimensions of 1 over length. So we want this to be much smaller than 1 over K. You can put it the other way around and say that K will be much smaller than 1 over L, with some very complicated algebra to derive that. Righty. If you do that, again, it's straightforward. You'll find that R, well, let me give you a bit more input. We have that in that limit, Q squared that we can see in there will be just alpha squared over L squared. That's what we assume is much greater. That will tend to alpha squared over L squared plus corrections of order K times L. In fact, that is our expansion parameter in here. That is our epsilon, so to speak. And, well, maybe we can already connect with what's to come. You can also define a mass scale from L which will be 1 over L. And then that same expansion parameter will be K over lambda, where lambda you can think of as the scale that suppresses higher dimensional operators in QFT. And that analogy is in fact what's going on in here, but in a much more simple setup. When you do that, you put that back in here. You get that this is 1 minus 2 KL. And also notice that Q times L, the square root of Q is alpha times L, so the L will cancel out to give us alpha sine of alpha L. No, sine of alpha, sorry. There you go. And the whole thing squared. And again, we write this up to higher correction zone powers of L, this small parameter, or the inverse of lambda, if you're trying to think about this in QFT terms. That will be what we call the EFT, the expansion in that parameter that we've identified. So remember, one of the pillars of the EFT is finding your expansion parameter. We have done that now. And even though we started with a full model, we can look at the low energy limit, we'll call it, or the small L limit, in which this is too small for you to resolve with your experiment, to look at what the theory looks like. Anything else we can glean from this? This is also what we call a model in that context. So we have the full theory in here, and we're taking a limit of that model. That will be the UV model, if you want, is the square well in this case. So now we'll do it over again with a different potential. That was 1, this is 2. Now with a delta function potential. Now we have the potential is again in our conventions. Let me get it right this time. Minus G over 2M L times a Dirac delta. In this case, our potential looks like an infinitely peak distribution around the origin. In fact, it's other than that being an infinity in the second derivative, that will mean that the first derivative will have a step on it. Other than that, it is an even simpler system. We don't need the intermediate wave function. It's just psi minus and psi plus, and the equations for us, for you to solve, are those boundary conditions, which are not simply they coincide at the origin, and that their x derivative represents that step. And if you work it out, it comes from Schrodinger equations. That will be G over L once you're taking those factors of 2M out. And I write, you could write it here either phi plus or phi minus. It doesn't matter because they're the same. Via those boundary conditions, that will return for you again T and R, which in this case are 1 over 1 plus 2 I K over L over G, the whole thing square, and T over 1 minus I E over 2KL. Very good. Again, you can solve for this yourselves. You can find it out for rather small effort. And we have another, something that is now what we call in our terminology a local term. It's infinitely localized around the origin, and it has no length to it, which is sort of mimicking the fact that in that small L limit, we don't resolve that small distance L. Still, it's a bit subtle now to find that the reflection coefficient square, which would for the full model still be 1 plus 2k L over G, the whole thing squared, can also be expanded on the small L limit to return 1 minus 2k L over G, or the whole thing squared. And I'm not going to write beyond that. Very good. So we've sort of done the same process and we expanded again, now with a somewhat simpler potential and a local one, which will be an analogy to the operators we have in there. Quite crucially though, in the EFT, we still expand. Really, to call it an EFT, you need an expansion parameter. Even though we could have the full solution to it, we're expanding on this as well. And we will expand also in the EFT, even if we could do some computations to higher orders. You have to be consistent and include everything at every level. Now, what I want you to do is to look at both results in that expansion for the original model and the other one we got. And realize that at this level, if we stop at order L squared, so to speak, they give the same result. Well, the physics is the same. There's a dependence on the wave vector squared times L squared. Only those coefficients look a little different. But if, let me put that in here, if I match them, if we look at matching, we'll say that this delta model can reproduce that, or this delta EFT, if you want to call it, can reproduce that square wave model if we identify G with what? Can you see it? An awakeness check, if you're looking at it. What will be G in terms of, I'm literally equating this term here, which hopefully you can read, 2k L over G, to this term here, 2k L over alpha sine alpha. Sorry? Alpha sine alpha, yes, yes. I know you all knew it, but I'm just trying to get you to speak often in the lecture. So there you go. Again, for rather a simple system, we have unveiled another feature of effective field theory. This is what we call matching. This is how we connect the low and the high energy theories. And we describe those, if you want, there's some sort of a universality, because if you have that expansion parameter, you'll have a Taylor series, and whatever your original theory, you'll be captured by the Taylor expansion coefficients in that, in those terms. And to this level, but not to higher levels, the delta function can reproduce the high, if you want, the UV model, that square well, with that matching condition, identifying G and alpha sine alpha. But now to highlight another of those points we remarked in there, we can spend a minute thinking about, well, what about it not being a square well potential? What if it looks something different? And we still do all of the same things. So that's what I'm going to talk about next, but any questions before I move on there? Good. I hope this is because you're following. So now, yeah, let's ask that question, which is very valid to ask, and also good physics to say, well, question whatever model you started with. So let me recycle this a little bit and say, yes. That's a good point. Yes, it's only for these powers of L in there that I can do that matching. What happens if you don't have, this is, by the way, related to what we call power counting, how to make the two things. So how many powers of L should it have? Well, Basically, we have as many powers of L as it will give us a local interaction at small L. But if you think of, say, I didn't put an L in here. So that was just a constant. And I just take L to be small. So what happens is you have a finite depth well that is going to shrink to a point, and that won't be C by the wave function. It just goes through without anything. So you want to still have something non-trivial left in that limit, and that's why we put that power of L in there. That's a good point. And that also is a good segue into other models that we could have in there. So as long as it gives something that in the L equal to 0 limit looks like a delta function, we can describe it that way. Or we could have instead say, why don't we have a potential that looks like this? I don't know, a couple of functions of different heights, as long as this is of a length L, and it also increases with 1 over L squared, or we take it to 0, it will also look something like, as we squeeze this, it will also look like a delta function. We squeeze it that way, but it would also be squeezed downward. Or we could have any other shape you can think of, and more, only the more creative you get, the harder it will be to solve analytically. But that doesn't make a difference to the basic physics concept that if you make whatever shape, whatever structure or UV model you can think of in there, as long as you can take that L going to 0 limit, you'll have a handle on a perturbative series that will be universal in describing those effects. And that is now the connection to another point in there, which is model independence. Okay, so some different people mean different things by this. Model independence in this context, and then the way I will talk about it, I'll think of it in two ways mostly, but the one I'm referring to right now is that you don't actually need to know what G is in here. For this local interaction and this expansion, you don't need to know what G is to do computation. You can just call it G, and then at the end of the day, if you want to talk to another series that actually has a theory of everything on a UV model, you can ask him, okay, what is the coefficient in the limit L equals going to 0 of your theory? I'll just match it to my EFT, and everything I've done will translate and apply to your model. But of course, 2 doors down, there might be another series with another model, but that's not a problem because you can again match it to it. So it's a good politics doing EFT. Yes. No, it doesn't have to be small. Oh, well, no, yeah, that's right. That's a good point. That's a good point, but that point is answered by this relation here. And actually, I was going to go to that at some point, which is right now, because you asked about it. But to answer your question with another question, let me, out of all of these theories, say, why don't I just, take, you're talking about Taylor series and expansions in K. Why don't I take a theory, let me call this, R for some theory T, that is just a K square term with some coefficient A, or if you want, 1 over A to get to your question. Now you can sort of answer it yourself. What would happen if I take A to 0 in this equation? What will go wrong? You see what I mean? Well, just to make it explicit, if I take A to 0 in here, I'll get that R is minus infinity. Hold on a minute. R plus T. Sorry, well, it's actually the square of something. So it's even worse than that. This is R squared, sorry. So that is the reflection coefficient. So it's already immediately problematic because you've said that something is positive on the left and negative on the right. What you've done is violated unitarity in there. And your theory breaks down after that. That is the way in which, in fact, in QFT, that's the way you can get a upper bound on couplings. Typically, this is, the couplings are not chosen that good, but in QFT, you'll have that this 1 over A is going to be some coupling in there, and you don't want this to be too large, or you will violate that bound. So in QFT, you typically have that. For example, the fine structure constant, or the QCD alpha coupling has to be smaller than something, and if we have time, we'll work out what that something is. But yeah, there's problems if you take some parameters too large and too small, and those couplings themselves are subject to constraints. But thanks for that question. Yeah, so there's sort of taking that limit, keeping L small but fixed, and then taking A to 0. So well, the whole thing has to be below 1, so yeah, there's also that avenue. We have 5 minutes. 15 minutes, alrighty. Good. So I think we squeezed out of this example as much as we could get. You actually went ahead of, I was going to ask the question about that, but you asked it yourselves, which is great. So let's look at a couple other examples, not in so much depth because we don't have the time for it, but they will illustrate some of the points about it. So this is, one of the points is we stopped at order k squared, and that looks like, in terms of potential, as a delta function. One could ask, what do higher order corrections, okay, fourth terms look like? And it's something that is not obvious from where we're standing, because what goes, okay, I take L to 0, that looks like a delta function. What could correct that on top of it? It should also be localized around the origin. Then what can it be that is not a delta function again? So for this, we're going to look at nuclear physics for a minute and form factors. You might be familiar with this from your undergrad, or that might have been a while ago and you've forgotten. So let me give you a lightning, it's not even going to be a review. I'll just give you the formulas. This is for non-relativistic scattering of an alpha particle of some nucleus target, mediated by electromagnetism. You have that the cross section for a solid angle, in this case, will be some form factor F of this change 3 moment. Let's call it K, like in the other case. K squared. Now this is a 3-vector, 3-wave vector. The whole thing squared, and then you have some constant, the fine structure constant, the number of protons in helium, number of protons in whatever nucleus you're thinking of, square, of course, and 16 times the energy of the incoming alpha particles, non-relativistic energy, and 4 powers of sine theta half. Where this form factor we compute if we're given the charge distribution of the nucleus as the Fourier transform of it, basically. Where f of x is the spatial charge distribution, it's called charge density. Normalized such that interval over 3 space is 1. So we sort of taken out those factors of the electric coupling and set for one and the other to make it slightly simpler. And I don't know, you look at a nucleus, it's going to be size around a femtometer, and those protons are distributed in there. Who knows what, how? But if you think of, maybe 3D plotting is a little tough, but if you think of X and Y, and the Z axis going to F, there will be some distribution of this charge centered around the origin. Righty. What does that distribution look like? Well, just a little bit more information to connect this to the Coulomb potential. That mediates the interaction. In this case, also to remind ourselves, will be just, again, fine structure constant, those set factors for the number of protons. And now the integral, or the solution of the Poisson equation, basically V3. This is now a function of, sorry about that, y vector is 3 space. I need another variable in here, V3x, or f of x minus y, the modulus of it. So we could also compute that Coulomb potential if we knew f, that charge distribution. Of course, this is just classical mechanics. But we're talking about a quantum mechanical scattering in that case. And again, something for you to work on. We don't know exactly what that distribution is. We can suggest a model for it. So let's take a simple model, which will just be a hard ball. That distribution f of x is just, we need it to be normalized properly, so it's going to be a 4 pi L cube, factor 3 in there, of 1 if the modulus of x is smaller than L, and 0. Okay, so L is sort of the size of this atom, this nucleus, sorry, femtometer-like. And that's another exercise for you. Do the Fourier transform of this f of x to obtain the form factor. Just to be consistent, I put a k squared in there because it's going to depend on the modulus squared. And you can get this expression. Again, there's a typo in the notes, I'll correct it later. You can use those to get f of k squared, 3 over k modulus of k times L squared, and sines and cosines to go with it. Okay, that will be the answer for a full model, and you know the drill now. We want to take the low L limit of this, that same L. If you cannot resolve it, you can expand it to find 1 minus k times L squared over 10 in this case. And you can work out a factor of 10 yourself. Right, so that's not something new. What is new in this case is that these two corrections, when you go back to position representation, so we're going around in circles now, not exactly, but we start from f of x for this hard ball model. We compute the Fourier transform. Okay, we get the exact result, and then we expand on k, and now we can Fourier transform back only these two terms, these two first terms, into f of x. So we Fourier transform that back, and again, that's something that you can check. Or in general, if you take an f of k squared, that is just 1 plus some coefficient c times k squared L squared. And you do the Fourier transform, you'll get, well, I mean, it's simple enough. If you put 1 in a Fourier transform, you'll get a Dirac delta, a 3 Dirac delta, right? I hope you've done that before and you know that. But the second term We'll also have that Dirac delta. What else? There's a k squared, which in position representation will be a derivative. So in fact, that will be, well, minus because of those factors of I, c times gradient squared on a 3 Dirac delta. What's more, you can push this into that potential there and see what that looks like. And why do we mean by these higher corrections? That will give you a potential that is proportional to, the details are in the notes, 1 over R, the Coulomb potential, and then 1 plus 3C L squared over R squared. So what we're doing with these higher order terms, we're sort of computing higher order corrections that in this case look like derivative on delta function. And when we turn this into a potential, this is the proportional sign, sorry. It will be actually for that potential corrections of 1 over R plus extra terms, like a multiple expansion. I'm just going to say a few words about the other model and let you go. But I had one question for the audience. Yes, so if you're following, the question for the audience is, so here in f of k squared, we had that the first non-trivial term is k squared, but there's no term linear in k. So have ingredient say, I don't know, a k vector times some other vector b. Can anyone in the audience think of why this original system we started with, the hard ball, or any system that looks something like that, wouldn't have such a term in, so this is f of k squared. Why do we skip the linear term in this case? Yes. Yes, the symmetric, who said symmetric? Yeah, sorry, I do want everyone to participate, so please do speak your mind. And again, it's not about being right or wrong. There's no vector in that hard shell. There's no preferred direction to choose from it. It's spherically symmetric, so there's no possibility for such a term in there. That's why it starts with k squared in that case. And right, so that's teaches us even something else about that list that we had in there. When you have a symmetry, the system or the description for it will either be simpler or constrained in the terms that you could have in there. So this is sort of forbidden by symmetry. And all of this has reflections on quantum field theory. But just to close it out, on the topic of identifying degrees of freedom, it's not always clear what are the appropriate degrees of freedom to discuss a given system. And an example that, in fact, I'm also taking in essence from David B. Kaplan's notes, but you can find about this in the superconductivity textbook or BCS instability. But when you start with certain condensed matter systems in which you're trying to describe the electronic structure of it, you start from, so this is going to be, what did I call this in the notes? Superconductivity. And Cooper pairs. You start describing a system by having you want to think of it as a lattice of ions in whatever system you have. And then some of the electrons of the outer shells are freely traveling around that lattice. And of course, those are fermions. They have different properties because they're in a medium, but they're fermionic in nature. And they do have interactions with the lattice that I can code it in terms of phonons. And you can, in fact, if you go to David Kaplan's notes, you can talk about the EFT of this as well and try to identify expansion parameters in it. And one of the realizations is that it's a certain limit in which, because of running, something I will discuss at some point if we have time. Well, we will discuss for sure. Because of running, that coupling to phonons gets stronger in certain limit. And it is an attractive interaction. And in fact, it gets so strong, or that instability drives the system to again, something like what was happening there, violation of unitarity, some very strongly coupled system that you cannot describe in the original degrees of freedom anymore. And what happens after that instability has developed is that the theory is actually best described by Cooper pairs, which are a sort of bound system of two electrons that are bound together by the lattice interactions. You can think of this quantitatively as the electron here pulling the positive electric charge towards it a little bit, and that attracts another electron far away. But these are the typical sizes across many entries in that lattice. It's really large compared to those, and that also explains why you get superconductivity in this case. Those bigger bosons, now notice that these two fermions will give a boson. We'll have a much larger size, and one of the things that increases resistivity of resistance of materials and stop those electrons are imperfections, but those are typically of atomic size. So these guys, because they're so much larger, they can basically sail through those imperfections and conduct electricity much more efficiently than your regular metals. So that's the qualitative picture of superconductivity, and why in this system is not obvious from the starting point, which is fermions, which are the actual appropriate degrees of freedom to describe it, which is bosons in that case. And that's actually great because I've covered everything I had in there, and it was a lot. So I hope you were able to get something out of it. But yeah, if you are pressed with time and can only do one thing, do that square well computation for the wave function and quantum mechanics. But yeah, I'll leave it there and take questions. I think I took a bit more of time, but hopefully that's okay. But yeah, any questions? It can have, right, it will have a linear, but it wouldn't be a correction to the Coulomb potential. So there's also, interactions proportional to spin and the dipole moments of that system. Those wouldn't look like this. They will depend on magnetic moment, and they would also be there. But that's a different term in your potential that comes out of electromagnetism. Yeah, this is just a simple system. I just wanted to show you that that term in there. Because there are some vector quantities associated to a nucleus, of course, like the dipole moment, and those are actually quite relevant for particle physics as well, because we can compute some of those from first principle. Yeah, so that's why you good. So that example is something that question is related to something that it's been mentioned already in particle physics. We call it the inverse problem, and that is to say, hold on a minute. At this level, you say that all of those potentials to leading order will just give me a k-square correction. So you want to learn more and more about what is the actual one. You'll need more and more terms in that expansion because they have, for example, different ratios. If I take the square well, or if I take a triangle like one, they'll have different ratios. But if you wanted to, learn about the microscopic full structure of it, you'll need arbitrarily many terms in that Taylor series. So that's what makes it hard to learn things about the full UV theory from low energy. You can learn a few things, and you can tell some raw features of the models, but you cannot tell them precisely apart. Yeah, so you could put in, yeah, so that will, indeed, if you do know the symmetries of it, you can already write your EFT reflecting those symmetries. And I kind of did that already without telling you, but I wrote in here that f of is a function of k-square only, not k itself. So because I already sort of knew that, I wrote that expansion as f of k-square. And in fact, if you know that from the beginning, you make your life a little simpler because you don't have to consider those linear terms, etc. But yeah, it's because that limit being valid, it also guarantees that you'll have an analytic expansion of on K square. And in fact, that's also, you know, an analyticity is something that was already touched upon in the lecture item. So it's related. Yes, so that's a good point. This, and that has to do with higher orders. So I only said that the delta function can reproduce the square well to order K squared. If you actually go and compute, because we have the full set of models, you can compute the next K4th term in there, and you'll find that you cannot reproduce the Dirac, the square well with the Dirac delta function anymore. This term is not going to be the same as that, because you sort of fix a relation between G and alpha, so that is fixed, and you can now predict those terms. The reason is that in this sort of context, there will also be higher order correction to that delta potential. In particular, we've seen what they look like in there with derivatives and delta. And now to match that square well, you'll need to add this extra term in your expansion so that the fourth power in K also matches between the two. That means you'll need another parameter C, and you have to fix that to alpha. But that in essence is, again, that's why this example it looks quite trivial, but it has a lot of physics in it. That is also related to higher order correction and how you need in the SMEFT, for example, if you start with dimension 6 and you want to do higher order corrections, you'll need dimension 8 to account for those next to leading corrections consistently. So I can rewrite it for you to see it a little easier as I realize now that my writing is terrible, but I can rewrite that. It's not obvious at all that this has a non-singular limit, because if I write LKL as epsilon, I'll have sine of epsilon over epsilon minus cosine of epsilon. Right, and like you said, this sine of epsilon over epsilon, at least the first term, is not divergent because sine of epsilon is odd in E and has higher powers. But not only that, the second order term in the cosine and in the sine should also have the right combination to cancel that epsilon square in there. So that's sort of going to happen anyway. If I do that explicitly, I'll have 1 over epsilon. I don't know, I should do that. I mean, you guys are smart enough to expand the sine and the cosine, so you can do that in there. The first order will be 1 in here, or sine of epsilon over epsilon. The second order will be epsilon cubed over epsilon. That's epsilon squared. The 1 in the cosine and the sine expansion over epsilon will cancel out. So then you're safe. Yes. So that's the answer to your question. There will be an epsilon squared term, and the next one will be order epsilon 4, so we're safe. Find typos in the notes. I find them myself right now. Let me know, and it's a work in progress. So I'm correcting the notes as we go.